And let me send you to practice quiz problem number 1. Give an example of the chain rule in 2 space as in calculus 1. So think of a problem where you're going to need the chain rule and then do it. Okay, 30 seconds more. So if I was taking the derivative of, let's say, 3x plus 4 to the 8th, I would take the derivative just like it was x to the 8th. 8 times the 1 out front and decrease the exponent by 1, but then I have to chain on the derivative of the internal. And then that derivative is just 3. And this extra 3 has to do with the chain rule. And give me a little feedback. Were you able to remember what the chain rule was and come up with some kind of example of that? And then, now a harder one. State what the chain rule is in its abstract form. As a rule, how do you write it? Okay, 30 seconds more. Alright, there's actually 2 ways to write it. This is a much bigger challenge. When you're taking the derivative of a function within a function, that's when you need the chain rule. See, if this had just been x to the 8th, no problem, didn't need the chain rule. Because it was a g of x function within an f of x, that's where we needed the chain rule. And you take the derivative of the outside. You leave the inside just the way it was. So when I took 8, I didn't take the derivative at this point. I just left the inside just the way it was. Okay. And then you have to tack on, so that is a function of that, and then you tack on g prime of x. Now, that's the way we conceive of it when we're executing it, because it's kind of helpful to think of it that way, as and it helps me step through the process. So I'm taking the derivative of like x to the 8th, but I'm treating it as, it's not x to the 8th, but 3x plus 4 to the 8th, leaving the g of x as the input. Now the other way to state the chain rule is dy dx. You get to pick an intermediate function, u. You get to pick u to be whatever function you want, any intermediate function that is useful for you. dy du times du dx. And remember, it was Leibniz and Newton that both created calculus simultaneously and independently. And Leibniz, he used this fractional notation because he said, hey, it's going to work like a fraction, like these two would cancel each other out, and so it'll help us to remember that. And so that notation is really useful to us in situations like this. Okay. Now, we don't usually think of this as how we're doing the chain rule up here. But this is conceptually how the chain rule is really formulated and what it really means. If we did it this way, let me do it in blue up here, you would do a u substitution. You would let u equal the inner function. So that's my intermediate function. Then, so we're taking d dx of u to the 8th. And then that's going to be, when you take its derivative, we claim that this is going to be 8u to the 7th, and when you take the du dx, but you see what we're really doing here, this was dy du. We're taking the derivative of the y. If the original was y equals 3x plus 4 to the 8th, then y as a function of u would look like this. Y equals u to the 8th. And then dy du would be 8u to the 7th. So you see that 8u to the 7th is really dy du. And then this is du dx. And these cancel out, and you get dy du. And this is, now do these in terms, replace the u with 3x plus 4. So this is 8 times 3x plus 4 to the 7th. And then the derivative of 3x plus 4 is just 3. And you're getting the same answer as we had before. Alright? Give me a little feedback on the way we state the chain rule. Alright, this stuff, today's section is going to be the chain rule. So this is background review knowledge to set up today's section. And this is from yesterday's work. Go ahead and find the first partial derivatives of f. Twenty seconds more for fx. Okay, so we hold the y as constant. So we think of 3 cosine y squared as all the constant out in front times x. So the derivative of a constant times x is just the constant. And then when we take the derivative of this, I need the product rule. I'm going to group this together. Times the first times the derivative of the second. Plus the second times the derivative of the first. So using the product rule. So this derivative is just e to the x. This derivative is minus 4. So I'm going to get minus 4x e to the x minus 4 e to the x. And that's going to be it. That's my fx. And let me give you just a quick minute before I do the fy. Alright, so the fy, this is constant, and so I'm just going to repeat that constant. The derivative of cosine of something is negative sine of that something, and then I have to chain on the derivative of the inside. Then the derivative of the second term is just all 0 because there's no y's. Now when I take this derivative, I get 2y, but this letter and this letter are different letters, so y is some function of x. So we got to do the chain rule, dy dx, like this. Hold it. Into old habits. This is dy, dy, because I'm taking the derivative with respect to y. and then you don't really need the chain rule. You just get dy dy. And so this turns out to be Fy is this 2 and this 3 combined minus 6 x y. This is just 1, and then sine of y squared. Alright, there's the fx, there's the fy. Give me a little feedback on number 3, please. And find the length of this vector, this space curve r of t within those limits.
I have a question. For the previous one is about the Fy. We take variable y. Variable is y, and when we do respect to y, is the first part is minus 6. Okay. The first part of derivative is 3x times 2 cosine y, and isn't it kind of a chain rule because it's cosine y squared? If you, if,
Yes. It's a
yeah,
chain
if
rule,
you,
that's why we had to have this extra part right here. Chain that on.
okay, so what I got is 2 cosine y times minus a sine y. I take it as a cosine y as a u. So
Okay. I think what you were interpreting it as is this. You were interpreting it as 3x cosine y squared. But that's not what it is.
Oh, okay, I see.
3x cosine y squared.
Okay, I got it.
If they mean
Yeah.
this, they write it the squared here.
Yeah, that's correct.
Okay? Thanks for asking.
Okay.
Make sure you got that clear.
Yeah, thank you.
All right, let me give a little bit more time on number 4. Okay, let me start on number 4. So the length, switch. When we're finding the length of a curve in 3 space, it depends and speed. If you're going 2 miles an hour for 3 hours, you are going to travel 6 miles. No matter whether you go around in circles, little tiny circles, or whether you go in a straight line. If you go 2 miles an hour for 3 hours, you're going to travel 6 miles. That's it. So this is the position, r of t. If we take r prime of t, we get, and then we take, now that's going to be the velocity. We take the magnitude of that vector, we get the speed. And the formula is the integral from one time to another time. That's the length of the curve. So we're going to work it out. So this is going to be the integral from 0 to ln 2. The magnitude, well, we first got to figure out what r, let me change color for a minute. I'll go to this one. R prime of t is the derivative of e to the u is e to the u, and then you got to take the derivative of the u with the chain rule. So it's 2 e to the 2t. The derivative of this one, the derivative e to the 2t will be e to the 2t times an extra 2, so it'll be 4 e to the 2t. The derivative of the 5 is just 0. The derivative of this minus 20 is a constant, or the derivative of that constant is 0. The derivative of this will also give me 4 e to the 2t. That's r prime. Now when we take the magnitude of that, it's the square root of the sum of the squares of the components. Take each of these components, square them. Dt. Okay, and then this is going to equal 0 to ln 2 of the square root. How many are we going to get? 4? They're all going to be the e to the 4t. You're going to have 4 of them, 16 and 16, 32, 36. Power to a power, you multiply. Okay, and then
wouldn't the t itself be raised to wouldn't the t itself be raised to a power of 2?
Good question.
Even though it's already in the exponent?
Even though it's already in the exponent. So let's do, I'm going to change color, a little aside over here. Suppose I had e to the 8th squared.
Oh, it's repeated it's repeated addition, so no, it wouldn't be.
Right.
It would just be e to the 16th.
That's right. So it would be 2t plus 2t, or multiplied together, you get 4t. That's right. Okay. So then we're going to get 6, and then the square root of this, square root is really the same as 1/2 exponent. And 1/2 of 4t is e to the 2t. Or you can think of e to the 2t times e to the 2t, add the exponents, and get e to the 4t. So that's the square root of that. dt. Now the 6 gets to come out in front. That's not a problem. To take this integral of e to the 2t, it's going to be e to the 2t again. Technically, you're supposed to do u substitution for this. But I like to just guess e to the 2t. And then there's a 6. And then I'm either going to be dividing by 2 or multiplying by 2 on this. If I tried multiplying by 2, for taking the indefinite integral of this, and then I kind of checked my work. Now, to check my work, the derivative of this has to get you back to this. But we'd get an extra 2. That 2 that I put in there, I put in the wrong way. It should have been divided by 2. So that when I take the derivative of this and get an extra 2, it'll cancel with this and it'll be back to this. Now this is evaluated from t equals vertical bar, t equals 0 to t equals ln 2. Now I could have put the 6 over 2 in parentheses, or I could have just factored them out. I like to factor them out. So this is equal to 3, and then when you substitute ln 2, you're going to get e to the 2 ln 2 minus e to the 2 times 0, which is 0. Alright, now 2 ln 2. This 2 gets to go up here as the exponent. So this is equal to 3, and then of course e to the 0 is just 1. Alright, when this goes up as the exponent, you get e to the ln 2 to the 2, which is 4, minus 1. Now, only when you have them exactly adjacent, because of this 2 was in the way, you couldn't cancel these out. But now, these are inverse functions, killing each other off. 3, 4 minus 1, which is another 3. 3 times 3 is 9. So, the length of this curve in this interval is exactly 9. And give me a little feedback on number 4. Is the review helpful, or you already had that down? All right, one at a time. Identify as a surface. It shouldn't be or, of, it should be or a space curve. So on A, there's a particular function, and this is an example of a function like this. So there's the kind of the general case. Here's a specific case. For both of these, is this a surface or is it a space curve? "30 seconds more."
For some reason, I can't tell if the sign between the Z and everything else is a subtraction sign, or okay, it's an equal sign. That's weird.
Okay. I probably should zoom these in a little bit more. Alright, so this is a surface. How do I know it's not a space curve? How do I know it's a surface? Because every single point on the floor, which is the XY plane, is going to get a height associated with it. You can pick any XY coordinate, and then you'll get a height associated with it. You build the dirt up to that height. Cover the dirt with a tarp. That tarp is the surface. Visual representation of our surface. Okay, let's go to the next one. Is that a surface or a space curve? Here's a specific case, here's the general case. 15 seconds more. This is a space curve. A little tiny rocket ship is zipping around in here and creating a curve in the 3 space. How do I know that's the case? Well, this is really an x equals. This is a y equals. This is a z equals. We don't have the entire xy plane as a domain anymore. You're only going to have very specific ones. When t is equal to 1, you're going to get 5, you're going to get x is 2. You're going to, when t is 1, y is going to be 3. And z is going to be e. Now this is going to be a specific point. It's the end of the vector, and that's a point on our space curve. And 2, 3, when x is 2, y is 3, that's that point. Go straight up E there. That's going to be it. But notice 2, 3 is there, but 2, 4 is not. When x is 2 and y is 4, we're not going to have a height directly above that. It's not. Because when x is 2, the y is going to be 3. That's it. For the x value of 2, you're only going to have, maybe 1 or 2 possible y values that you're going to have. You don't get the entire xy plane and heights with each one of these. You get a very limited space curve. All right. Now let's go to C. Now, this is like this. Z is a function of x and y. So it's this general case. X is a function of t. So it's some g of t. Y is a function of t, like some h of t. Now, putting all that together, is this a surface or a space curve? And this one is not so simple. I'll give you a minute. Alright, now since this one is much more complex than the first two and new to us, I'm going to ask, does anybody have any insight that would lead me into deciding whether this is a surface or a space curve.
I would say we should look at the domain of some of these functions. So like, if we're looking at the values of t, assuming t can be anything,
Yes, it can be
I think, and depending on what the functions g and h are, I would say that it is possible that the domain of the function f is all real numbers. And if so, then we've got the same case as problem A.
So
I think
Not the space curve.
I think it would be a surface,
Okay.
like a parametric surface, basically.
And Cameron, what were you going to say?
So as long as z is a function of the other two, as long as the value of z is a function of the other two components, I think we have a surface. Whereas in a space
Z
curve,
is like this one, and as long as that's there, it has the components of a surface.
yes.
So both
And
of you are agreeing.
okay.
All right. Anybody else?
I would also say that would have to be some sort of surface, like a parametric surface, like Rowan said.
Okay. Well, let's look at this. Let's let t be 0. Then x is going to be -1, y is going to be 0. Now, can you get, so if x is -1, it's back over here. It says when x is -1, y is 0. Could you ever get when x is -1, y is something else, like y is 2, or y is 3, or anything like this? No, the only way I can get x to be -1 is by taking the t to be 0, and then the y can't be anything else. Similarly, if x is 1, you're going to get 4 minus 1, you're going to get 3. You're going to get 7 minus 2, which is 5. When x is 3, the only way to get x to be 3 is let t be 1, and then the y will only be 5. You'll never get any other value. When x is 3, the only point in the domain on this dotted line is that one, right there. The domain is not the entire xy plane for this. It would have been the entire xy plane if these two dudes weren't parametrized in terms of t. But when they were parametrized in terms of t, we're going to get very specific. This is, in fact, you can put these two together, remove the t from them, parametrically defined, and you make a regular Cartesian equation, you're going to get some kind of a parabola. And it's only directly above this or below this parabola that we're going to have heights. And this is not a surface, but a space curve. When only this space curve doesn't, see, the essential difference is a surface, the domain is the entire, as Rowan was saying, focus on the domain. If you can get the entire xy plane, you're a surface. But if you're only a specific curve in the xy plane, and then only heights on that, then you're getting a space curve.
Okay, this is something that I'm not exactly following. The range of a function is what a function can legally output. whereas a domain is what can be legally input into a function, correct?
Correct.
I see no domain restrictions on the, I see no domain restrictions on T.
There are no domain restrictions on T, but the T limits what the X and Y can be. These wind up limiting what the X and Y choices are over here. When the X is 3, you only have one choice for Y, which is 5. Because although T gets to be whatever it wants, you're not going to get all the different values over here. So,
Okay.
all right.
Okay.
The I think there was something else I was going to say, but I can't remember it. All right. I'll just put this on here. Restricts choices for X and Y. And because of that restriction that this is going to cause, it causes us to be getting a space curve, not a surface. And it's tricky in here, but this is pretty important to get this idea, to understand what we're going to do today, chain rule in 3 space. Okay. Any further questions on this? Or am I good to move on? All right. Questions on homework or on anything?
Stated earlier in the text chat.
Okay, could you tell me out loud? Give me one problem.
I have problems figuring out. I have problems with distinguishing the process needed to find the speed of something moving along a trajectory versus actually finding the trajectory. And so that doesn't apply to a specific problem, it applies to a class of problems.
Okay, so the issue is finding speed. Is that right?
I can't seem to tell the difference between it and finding the length of a curve for some reason.
Oh, okay.
So I could tell you how long a trajectory is, but I couldn't figure out a way to tell you what the speed is of the thing is at a particular point on the trajectory.
All right, let's go back to our example over here. I'm glad you can articulate your questions well. So the question was find the length of this curve. And we got a specific number, which was 9. Okay. Now, the speed on this curve at any time turns out to be right here. No, this isn't the speed, this is the velocity. And notice the velocity,
Still has direction.
yes, it's got direction. And the direction that it's pointing is the direction that you're instantaneously heading at
Yes.
that particular time. And then if you took its magnitude, and then when you took the magnitude, you get what? 6 times e to the 2t. This is the speed.
So I find the speed in the process of finding the length of a curve.
That's right.
Oh, well, I suppose that does make my life considerably easier.
Yes. The speed is a necessary ingredient to find the length of the curve. And so I can see how you can get these two things kind of overlapping and mixed up a little bit. You got to find the speed as an intermediate step to get, because this part right here is the speed.
Okay.
Does that clear it up for you, Cameron?
Yes, that does.
Okay. Other questions?
I have a question about limits of multi-variable functions. So, yeah, I guess it was on Monday, we kind of talked about some examples where we're approaching the point 0, 0.
Yes.
And in that sense, it made sense to like approach from the x-axis and then the y-axis and then compare those two values. But when we're approaching a point that isn't 0, 0, I don't think, can we still do the y-axis and x-axis trick, or do we do it a different way?
But there's typically no need. You'll get
Does that make
exactly
sense?
the same value no matter how you approach it. The only time you'll get different limits is if there's some kind of discontinuity happening there. And that one shape that we had, it was like, you know, a sheet of paper that had been torn and then folded in this kind of crazy way. Did I answer your question, Ron? And I can't hear anything now. I had this problem earlier today. I was in a Teams meeting and I was kind of going in and out. Alright. You can use the text channel too if you're not able to talk. Anything else? Any other questions? And Rowan, did I answer your question okay? If you can hear me, if you can just text whether that was all right. Okay, Rowan's internet. Maybe it's Rowan's internet. Okay. And if there are no more questions, well, let's move on. And I got to close this out and open it back up again. After a while, it quits working right. All right, so let's go to 15.4, the chain rule. And let's review the chain rule, the old chain rule in 2 space. And the point I'm going to make here is, hopefully this will sync. There we go. The point is that it's an incredibly obvious rule, an incredibly intuitive rule. So much so that you don't really need a proof of it. It'll jump out at you if you can see it in the right way. So I'm going to use an example. Hopefully that'll show you this. An example where we're going to use the chain rule. Let's suppose y is a father's position. X is the pregnant mother's position. Um, oh, let me change it. Instead of calling that one x, let's call her u. And then x is going to be the 3-year-old position. Alright, so in this family, if we did dy dt, can anybody tell me what would dy dt represent verbally? Same with du dt. And dx dt. Yep.
The function of whoever's position as a function of t.
Yep. Father's position. Now these are all going to be functions of t. But what about their derivatives? What would it represent? I'll give you a quick hint.
Change in father's position with respect to t.
And what's another name we might give for that?
For t,
For dy dt. The change in his position.
with respect to the number of bananas he eats.
Okay. With respect to time. Suppose we were measuring.
I was hoping to avoid that one.
Okay. Suppose y was in, the position was in feet and the time was in seconds. And then this would give us how many feet. Remember that we say the derivative represents the change in the output every time the input increases by 1. So change in how many feet he's traveled, change in position per second. So it's feet per second, or if we had done it in miles per hour, it would be miles per hour. And all of this is the father's speed or velocity if you didn't take the absolute value. Well, let's just keep them all positive, so it's speed. So it's how fast the father's going. And then how fast the mother's going, how fast the 3-year-old son is going. That's what these things represent. Okay. And if we had the suppose we weren't able to get these things objectively, we were going to have to work with these things. Suppose we wanted like dy father's position versus the son's position, dy dx. Now, what would this represent if we were doing the same kind of thing? Now this would be how many times faster. So every time the child moves 1 foot, the father moves 3 foot, then that would be the father is how many times faster? The father is. And the, let's say, daughter. Okay. So if it turns out to be like three times as fast. All right. Now, we might be really interested in these ratios, particularly if we couldn't get these ratios. Like, suppose you didn't have a stopwatch, and you didn't have a timepiece. Then you can't get these other things, but you can still get these kind of things, these relative measures of this. All right. Now, if you wanted dy dx, but the 3-year-old daughter is too smart. She won't race against the father because she knows Dad's going to beat me real bad, so she refuses to. So, but this, I suppose this is what we really wanted. We wanted to get dy dx. What could rescue us is this. We could still get dy dx even though we couldn't get it directly. We could get it indirectly. The pregnant mom can race against the dad. This would be, and now, how many times faster the dad is than the pregnant mom. Suppose this turns out to be 2. So let me insert. And suppose this was 2. And then now 2, and let me just make a note. Or no. Dad is twice as fast. As mom. Alright, now the mom is the intermediary, and the daughter will race against the mom. Thinks she has a chance against pregnant mom, but pregnant mom surprises her. And this turns out to be 3. Mom is 3 times as fast as the pregnant daughter. Or the pregnant mom is 3 times as fast as the daughter. So that tells us that the dad is 6 times as fast. We'd multiply these 2 together. 6 times as fast as the daughter right here. And this is the chain rule in Leibniz's notation. He said it'll work just like a fraction. These du's would cancel out, but just like dy dx. And you can use any intermediary you want. And as long as you compare here and here and here and here. So the chain rule, the point I'm trying to make is that the chain rule is when you see it in this form, which is not the form that we usually use when we think about how we execute the chain rule. We usually think of it like this when we execute it in symbols. But in theoretical construction, this is the way we really think of the chain rule. That's just for how we execute it. And this way is incredibly intuitive. It's just that you can just pick any intermediary you want. And this is a very strange rule as well, because look at, there's no U on the left-hand side. The U comes out of nowhere. When a new letter comes out of nowhere, it means you can pick it, whatever you want it to be. And so it's some intermediary function that we're going to use that we find useful. Like we got to pick, oh, we think this would make a useful thing right here, but we could pick this U to be whatever we want. All right. Give me a little feedback on intuitive feel for the chain rule, and then we'll take a break. Does this make sense? Does it give you a little better feel for the chain rule in general? Yes.
No, not really. Because while with the example that you've just given, you've said that we can't directly find how many times faster the father is compared to the daughter, because the daughter's not going to. I like that you used an analogy, but what I do not figure out from this analogy is how is it really that the mother? Why is it that? How is it that the mother compares to? It seems like the only way the mother compares to the father in this case is because because somebody said so and it was so, sort of, so to speak.
All right. When you take dy du, when we interpret the derivative, it's the change in the output every time the input increases by 1.
Yes.
So when this goes up 1 foot, this
Yes.
is going to go up 2 feet. So the father then is twice as fast as the mother.
Yes.
Okay. And then the reason why this, so the child moves 1 foot forward, the mother moves 3 feet forward, so the mother's 3 times as fast. Now this is assuming that it's a constant. So we're kind of, saying that, the maximum speed of the dad, and he can maintain it for a short interval, is this. So I kind of oversimplified things. If it was, where the variable speed, then it would be more complicated. But I'm trying to pick a really simple one to give you the kind of the essence of the intermediary function.
Okay, but how do we know that we've picked the right intermediary function?
It doesn't matter. You don't have to pick the right intermediary function. It's any intermediary function can do it. And we, on this problem up here, we only picked the function u to be 3x plus 4 so that we could rewrite y as u to the 8th, so then this dy du would be a nice easy thing to do right over here. But we could have picked them different. Any intermediate function, the relationship would still hold true. dy du dx, multiply them together, you get dy dx. Even if you can't compute what dy du is, and even if you can't compute what du dx is, it still holds true.
Okay.
Okay. And makes some sense. Okay. If you get any more questions that would add some clarity to it, and I'd be happy to look at those later. Let's start again though at in 15 minutes. Start again at 6, so 46, 6:51. Anybody need to speak to me before I take my break? salad from yesterday. Mom was thinking, the tortillas with some of the potatoes. So the potatoes are in here. Yeah, there's 3 left. Alright. And then, there's some other leftovers. Do you have a good deal? Okay. And, you want beans with the burritos? Let's do it. Black beans. Nice. Sure. Alright. How about we warm these up? Getting close to spring break here. After this class tonight, I have 1 class tomorrow. Okay, we'll get started again here. And all right, one of the questions that would have bothered me, though, is if Dad is twice as fast as Mom, and Mom is 3 times as fast as the 3-year-old, then how do I know that I'm multiplying these two numbers? Why not add them? Maybe Dad is 5 times as fast as the child, not 6 times as fast. And anybody want to offer up a possible explanation of why we say it's 6 times instead of 5 times as fast?
Well, we know that since if one of them's going 3 times faster than the first one, and that second one's going 2 times faster than that, it has to be 6 times, not 5 times.
Okay?
Just kind of logically thinking.
Okay, we keep using the word times in there too, so it would make sense that we'd times them in here as well. Anybody else? All right, let me offer 2 possible explanations for this. One is kind of a chain reaction. I think it's called the chain rule because of chain reaction. Let's think of the child as moving 1 foot. That sets off this chain of the mother moving 3 feet. Now, if the mother moves 3 feet, the dad then moves 6 feet, because he's got to be twice as. So all from that one chain of the child moving 1 feet, and then everybody moves at their maximum speed, then this one's got to go 2 feet, 3 feet, and this one's got to go 6 feet. So if we did it 1 foot at a time, chain reaction type of thing, we get that. The other justification that I sometimes use is, I think, well, what if all of a sudden we double one of these things? If instead of 3 times as fast, it's the mom is moving 6 times as fast as the child, then how is that going to influence the whole output? And if you double one of these, should the whole thing double? And the answer is, with that chain reaction kind of thing, if this one takes 1 step and this takes 6 steps, then yeah, the whole thing should get doubled. And that only will happen when you double one member, you double the output in a product. It won't happen in a sum. If you're adding 2 things together, you double one, it doesn't double the output. Now, let's come down to here. I have a question, and I want you to work on this in your groups. So, if the change in z is equal to 2, when the change in x is 1, if the change in z is 3, when the change in y is 1, what is the change in z when both x and y increase by 1? So, go to your group chat, and any ideas you have, start putting them in there, and I'll give you all a minute, and then I'll call the group. 30 seconds more. All right, group 2, what do you have?
We thought it was, I thought and Matt both thought that the change in Z would be 5 because we are adding the changes of because this because we were looking at a sum of changes, not a product. So X and Y are both independent variables, while Z is the dependent variable.
So you're seeing it not as a chain reaction like before. And so
Yes.
since it's not a chain reaction, you think they're going to add together instead of multiply.
Yes.
And group 1, do you agree with that?
I didn't yeah, that what Cameron just said makes sense to me. But that's not what I initially thought.
What did you initially think?
Initially I mean I think I answered a different question, but I said like dz dx is equal to 2, dz dy is equal to 3, so dy dz is 1/3, and then dx dy or dy dx is then therefore 2/3. But that's not even the right answer to that problem. So
Okay.
yeah.
I can kind of see your line of reasoning.
Yeah.
Okay. All right. Now, let's go from this to look at this example. This situation would be satisfied by exactly what's happening here. If the x increased by 1, the z would increase by 1. If the y increased by 1, the z would increase by 3. So we see these relationships happening with this equation right here. And so when both of them increase by 1, we're going to get exactly this answer. And the distinction that you're making is really important, that this is not a chain reaction. I like the way Cameron said the x and y are independent. So it wasn't one thing causing the other, which then caused the other, like we were seeing with the chain rule. We're going to wind up with a little different version of a chain rule because we're going to have some things that are independent, x and y, like this. Alright, so we're starting to differentiate some things. Chain rule, in general, that we're used to, everything was always multiplied. But over here, you can see we might be adding some things in functions of, in 3 space. Alright, now we got this really sophisticated problem. Well, let's keep it big for the reading of it, and then we'll have to see the chart afterwards. Alright, so the speed of sound traveling through ocean water with salinity 35, so how much salt it has. Okay, so it depends on how much salt, so they're holding the salt constant. Okay. The speed of sound is c, and it depends on the temperature T. Alright, these are up arrow, t squared, and t cubed. Copied these in, it didn't take those. Alright, so notice how the speed of sound depends on the temperature of the water and d, the depth below the ocean surface. But c's dependent on temperature is a very complicated expression. It's not necessarily like, when you have higher temperatures, the speed of sound in the water is faster. Because you've got a negative component with the squared, a positive component with t to the first, and a negative, or a positive component with t to the third. So it's a complex relationship, some kind of a wavy relationship with temperature. But the constants, the speed of sound's relationship with the depth is nice and simple. The deeper you go, the faster the speed of sound. So d is meters. Every meter you go deeper, you get 16/100ths faster speed of sound, or 16/1000ths added to the speed of sound. Right. So then, a scuba diver began a leisurely dive into the ocean water. The diver's depth and surrounding water and the surrounding water temperature over time are recorded in the following graphs. Look at those graphs in a minute. Estimate the rate of change with respect to time of the speed of sound through the ocean water experienced by the diver 20 minutes into the dive. And what are the units? So let's look at these two graphs. So on the temperature one, this axis is time in seconds, and this axis is the temperature. Okay, and here it's time again. And this axis is the d, the depth. Okay, and let's zoom in on one of these so you can see it a little better.
This is the temperature, and this is the with respect to the diver of the environment with respect to the diver. Correct?
Correct.
Good.
Just tracking with the diver. So in this one, the diver when it gets to 5 seconds and then all the way to 40 seconds. Okay. So at the beginning, the temperature was, this was about maybe, almost 16. And then as time goes on, the temperature is dropping. And then the temperature kind of levels out and then slowly drops again. And it's, 2, 4, 6, 8, 10, 12, 14, and that's 16 up there. So, the temperature is varying between about 16 and 10. And the depth. So they were tracking the diver, and the depth below the surface at time 0, it was right at the surface. And so you kind of have to think of this, upside down in a way, if you want to see, how deep he was. As time goes on, he went deeper and then came back up a little bit, not quite so deep, and did a deeper dive and then came back up. Okay. And Let's go back to the question. Estimate the rate of change with respect to time of the speed of sound through the ocean water experienced by the diver 20 minutes into the dive. This portion is telling you to find, and that's what I want you to complete right now. Find what, use symbols, mathematical symbols for what you're being asked to find. And when you get that, type that into your group chat. And don't type it in quite yet. I mean, you go ahead and type it in, but don't hit enter quite yet. Let everybody have some individual time to process this.
Can you scroll down a little bit so we can see the other graph?
Sure. I'm not asking you to estimate what the answer is, so you don't really need to see the graph. But what is it asking you to find in symbols? Go ahead and type it in. Go ahead and hit enter, and I'll give you just a little more time. Okay, group one, what's it asking us to find?
It's asking us to find the change of the speed of sound with respect to the depth and the temperature. So like, I guess I would say like dc over dt comma d, or something like that. It's like a derivative of two variables on the bottom.
Kind of like this?
Yeah, that's kind of what I had in mind.
Okay, you're on the right track.
If I may,
Yes.
I think we're looking for dc over d time, ultimately.
So how do I write it on the bottom?
Actually, shouldn't it be dc on the top?
DC on the top. Okay.
And then
I use
Then-
lowercase t on the bottom to like separate it from the capital T of temperature.
C, and then, yeah,
DC
cursive T.
little t. This is what we're really being asked to find. And I'm glad, Rowan, that you suggested this, because it'll help us differentiate this. C is really a function of T and D, temperature and depth. And temperature
and depth are a function of time.
these are both time functions. Okay, now this might be some G, this might be some H, okay, and when we did this, this is kind of my instinct when I'm first looking at this stuff too, is the derivative with respect to both of these things, but these would have to be partial derivatives. And we could only do them one at a time. If there's more than one variable, we got to use the del symbol instead of the d symbol. And there's two different possible partials instead of this. But what we're really being asked is estimate the rate of change, speed of sound through the ocean, and estimate the rate of change with respect to time. It's just this that we're asked to find. Now, this hopefully should get a little bit familiar, feel a little bit familiar from our practice quiz. When we were looking at this three-space surface, space curve. This is now the C with respect to T and D, but each of these, T and D, are functions of time. And this is actually now a space curve, not a surface anymore. Okay. So, just so far with this problem, we're just looking at what are they asking us to do here? When they ask me rate of change, that means derivative. And then we did this. And we see that this is kind of like the practice quiz problem. All right. Now, there's one other thing I'd add to this. They don't want us to find dc dt everywhere. They just want us to find it when time is 20. So I'd put a vertical bar evaluated at t equals 20. You can do it with a vertical bar, or you can do it like this. Of 20. I prefer the vertical bar kind of a thing. And that's what we're really being asked to find. And so now, let's go to the next thing. Question. If, in an abstract case, z is f of xy, and x equals x sub t, y equals y sub t, where z can now be thought of as a function of t only, because you could, just way back over here, if you knew what the g of t is and the h of t is, you could substitute those in for the t and the d up here, and then c would just be a function of little t, and that's why we didn't have to put a partial c with respect to t, because c can be thought of as a function of just the one variable, little t, and so you get to put a d. But when you think of c in terms of t and d, you have to have both, so that's why these have to have partial derivatives. So, back to here. Question. If z is this, x and t, x and y are in terms of t, z can be thought of as t only, then is the following true? dz dt is dx dt plus dy dt. So, say yes, it's true, or no, it's false into your group chat, and don't hit enter quite yet. Let's give a little bit of processing time. Go ahead and hit enter. Talk it out. All right, I think somebody's got their mic open. Cameron, if you can close your mic.
Sorry about
You're typing away. All right. All right. Group 2. Is this true or not?
Okay, I'm not completely sure, but I think it's false.
You think it's false?
with all the prior examples that we are given, this relationship is true. However, you mentioned something about the chain rule and how derivatives can chain into each other if they are, if one if the derivative is kind of directly linked to the parent function which we're looking for.
Okay.
So if dx actually does have a direct relationship with dz, then the following would no longer be true.
All right. So it looks like it's missing some kind of a part of the chain rule. Is kind of what I'm hearing you saying. And let me check in with group 1. What's your instinct?
It was kind of split on our side. I think it's false, but I Sue thinks it's true.
Gotcha. All right. This, to me, I'd be kind of a little bit torn. I think I'd feel, if this is the first time I was seeing this, I'd kind of see, there's got to be some kind of relationship like this. But typically in the chain rule, there are things that would cancel out that are multiplied together, and I'm not seeing that over here. All right. To put flesh to this, let's look at an example. And we're going to look at example A, which is going to be z equals x times y, where x equals 2t and y equals 3t. Kind of big on 2 and 3's today. And then we're going to look at example B, where z is equal to x to the 100th power times y to the 80th power. A way bigger function than this one. And x equals 2t, y equals 3t. Alright, now, let's suppose we use this. dz dt is dx dt. Well, look at right up here. dx dt is 2. dy dt.
Both cases it's false.
Yes. dx dt is 2. dy dt is 3. And we'd be getting the same thing no matter what the function was. You see, this can't be right. It is definitely false. It's not even asking us what's happening. It doesn't even involve the z function over here. So this is definitely false. So if we could modify this so that it was actually true, how would we modify it? So let's make this true. dz can be thought of as a function of t only, because you could replace x with x sub t, with just t's and y's with just t's, and then z would be a function of just t. Now, what would go in front of this dx dt if this were really true? Anybody have any ideas?
No.
All right. What we need is a link to the z function, because if we don't have any link to the z function, then it doesn't matter what we put here. We're going to get exactly the same thing, 5, and that can't possibly be true. When t goes up by 1, what happens to z? When t goes up by 1, the x is going to go up by 2, and the y is going to go up by 3. But we need to know, well, what does a 1 unit change in x cause to happen to z? And that's going to be a much bigger change over here. What does a 1 unit change in x? Now we know x is going to change by 2. When t goes up by 1, in both cases, x goes up by 2 and the y goes up by 3. But we need to know what the z does. How does the z change when the x goes up by 1 over here, which is a much bigger change than how the z changes over here when the x goes up by 1. So we need the change in z times the change in x. Now, what does this mean? It is what does this mean? All right. I like to describe it this way. How many
Change in x with
unit increases in x each time t increases by 1? And notice that's going to be 2. T goes up by 1, you get 2 unit increases in x. And each unit increase is going to have an effect on z. How much the height changes each time x is increased by 1. If we think of z as the height above the xy plane, how much the height changes each time x increases by 1. But that's going to happen twice. And then if we continue on, we're going to have dy dt over here.
We're going to have to get rid of the addition sign sooner or later.
dz, del z, del t. Now why would we have to get rid of the addition sign?
Because we don't know if changes in x with respect to t are added with changes in y with respect to t.
That's going to go back to this kind of thing. We're going to have two different things happening, and they are going to have a summative effect. And it's going to be a plus, and it's going to stay the plus. Okay? Both of these
In this
things
case,
are
yes.
independent independently, well, they're kind of not necessarily, there's a part of it that's independent and part of it's not. Oops, I made a mistake here. Let me fix this. This was Y. So a similar explanation is going on in this. This is how many unit increases in Y each time t increases by 1, and then how does it affect the z every time there's a unit increase in Y. And so we're going to have both of these things added together in here. And this is the three-space chain rule. Now, if you only had a function and this was not defined in terms of t and that was not defined in terms of t, then there's no chain rule. Only when you have both of these things happening, where z is a differentiable function of f and y, and x and y are functions of little t. And then, let me scroll all the way up to the top.
And we get a curve in 3 space,
That's
not
right.
a surface.
Not a surface, then we're in this situation. We're at a space curve, and then we have a new chain rule. So it's a specialized situation when we have chain rules in 3 space. Not always. This one, there's no chain rule. Okay. And we see the form of the chain rule now. And what's cool about this is that it acts like fractions do. It's like we're getting dz dt again. And then another. But there's 2 contributions to the dz dt. One from making the x increase by 1. When t set off the chain reaction, it caused a change in the x, and then it caused a change in the y. All right. Now, let's go back and let's finish these problems in A and in B. Now we can actually do it. According to this, let me go to black. D Z dt can be computed. It's going to be partial of z with respect to x. How sensitive is z to a 1 unit increase in x? And how many 1 unit increases in x will be spawned by t increasing by 1? How sensitive is z to a 1 unit increase in y times how many 1 unit increases there are in y? Now, the partial of z with respect to x is you take that right here, you treat the y as a constant, and you just get partial of z with respect to x, you get y. Partial of x with respect to t is 2 plus partial of z with respect to y, take the derivative, and that's a constant, and you just get the constant. And this was 3. So dz dt is 3x plus 2y. That'd be it. When we use the chain rule correctly. And over here, we're going to have the same expression. So let me put it here. But the partials are very different. When x increases by 1, now this is going to be 2 and this is going to be 3, but when x increases by 1, it sets off a huge chain in z. How big of a change? Well, this becomes part of the constant. So it's going to be 100 y to the 80th, x to the 99th. And then that's the first part. And then the x dt was 2. Plus, and then dy dz is 80 x to the 100 y to the 79. So you decrease that by 1 times dy dt, which is 3. And so you wind up getting this big expression, way different than this answer, which now feels a lot more comfortable than getting 5 for both of them with this wrong formula. And okay, also with this, now that we're equipped with this, we could go back, we can find partial derivatives given two different things like this, and that's what much of your homework is going to be. Problems like that, but we could also now come back to this, and we could now answer this question. So, let's get a little space in here. We need to find dc dt evaluated at t equals 20. Alright, let's go back to this and let's find dc dt. Well, it's a function of t and d, and these are the other things. Now these are only given in graphical form. But this, we can go like this. dc dt is equal to the partial of c with respect to temperature times dt d little t plus the partial of c with respect to depth times the derivative of the depth with respect to time. That's the general equation for dc dt. Now, the delta c delta t we can compute from this. Let's take, I'm going to blow this up a bit now, come over here. Partial of c with respect to t. Derivative of constant is 0. Derivative of 4.6t is 4.6. Minus 2 times this thing. Let me pull out my calculator. 0.055 times 2 is 0.11. T to the first and then 0.00029 times 3. Alright, so it's plus 0.12387 t squared. And then the derivative of this, that's just a constant relative to t, so we don't have that. So it's just plus 0. Now let's do the partial of c.
Actually,
Yes.
are you sure? Are you sure we just drop it off? Last I checked, because d is its own thing, and we're looking at the partial to t. Shouldn't it just be added on to the rest?
Ah.
So shouldn't it be
No,
4.6?
because it's kind of like treated as a constant, so it just goes to 0.
And so what you're looking at, you can look at it this way. What does each part of these, how does it change when the temperature increases by 1? When the temperature increases by 1, this thing doesn't change. So that's why it's derivative of 0. Temperature increases by 1, this increases by 4.6. This depends on what the temperature was, this one depends on what the temperature was, and the depth won't change by increasing the temperature. So that's why it plus 0. And also what Matt was saying, it's just as a constant. Yeah.
Then there's something I do not understand from far earlier, from a little bit earlier, before we scrolled back up to this problem. So if we scroll back down to x to the 100th and y to the 80th power, and look at the partial for those, basically what I understand is that if we are looking at the partial of those, my understanding is that for the partial of for the partial derivative of I think it was z with respect to x. Well, basically, we should just forget. We should just basically leave off y to the 80th power because y doesn't change. Because y doesn't change. With every change in x.
We think of this, if you were thinking of like 523x to the 100th power, all right, then the partial, the derivative of that, you take this times this and you get x to the 99. Now what we're going to do is replace this 523 with y to the 80th, but treat it just like it was a 523. It's a constant. So you're going to get 100 times that times x to the 99.
Okay. Okay, I got it.
All right. Glad you asked. It's important to get those basics down on this. And all right, so we come over here, and
the constant is not a factor of one of the things.
Right.
It's not a factor of t. Okay.
And so this one, everything is 0. The only thing that changes when d increases by 1 is this, and it's 0.016.
Good.
That's it. All right. So we got these two things that we're going to come in and replace these two. So dc delta c delta t. No, these are d's. Sorry about that. dc dt is equal to, now replace this with this. 4.6 dt dt. How do I replace this? I look, now I can't really get an expression for this. I can't at all because it's just from a graph. This formula, I'm going to have to do something. I'm going to have to evaluate this at t equals 20. And then everything over here is going to get evaluated at t equals 20. All right. Now, when I do that, so these cap t's are going to have to get replaced with something. We'll find out when little t is 20. We're going to, what are the cap t's going to be replaced with when little t is 20? Well, we look at this graph right over here. When the little t is 20, so 5, 10, 15, 20. This one is 12.
4. Oh, yeah.
So cap t is going to be 12. And we're going to next go to dt, d cap t, d little t. We're going to put its result right here. And how do I get that? It's only at 20. So I look at 20, and what I'm trying to find now is the slope, the instantaneous slope. I'm going too low. It's almost 0. It's just barely downhill, huh? So I just kind of go like this. So by the time I move to the right, let's say 5 more units to 25, I drop from 12 to, just a tiny bit, when it's going to be really small. dt, well, why don't we just do this? Why don't we just call it 0? Because it'll be really close to 0. At 20, well, let's say negative 0.01. It's going down very slightly. And then plus dc dd, which was 0.016, times dc dt. Let's do this in green. dt. And I have to look at this graph. And zoom back out. All right. 5, 10, 15, 20. All right. When t is 20, this is going to be the d is almost 4. So let's say it's 3.7, something like that. And the slope. I make a tangent line here, and then I'll have 2 points to consider. So as I went from the change in the y is going to go from 2, 4, 6, 8, from 2 to 8, two to 8 is 6. The change in x is from 15 to 30, which is 15. Divide by 3, 2/5, or 0.4. And this is a positive 0.4. Now the actual value of d we didn't need because it wasn't in here. And then you plug these numbers in, and then you're going to come out with an actual number, and that number is my answer. And we've run out of time, and the homework is
Next week is spring break?
15.4. Yes, next week is
Oh.
spring break. Have a great break.
Mhm.
And one last thing I wanted to say before I let you go is if we were in 4 space, if z was a function of x, y, and w, then you'd have an extra term here. Like this. 3 different components. A change in t increased by 1 would set off 3 different changes, and you'd have to incorporate them all. And any questions or comments? We'll stop here.
Thank you very much.